Good morning. I know today is October 3rd and it's morning. So if you're watching this later on, good whatever time you're watching it. I promised this yesterday based on a discussion I had after most of you left. Basically, I was with three of you. And I remember the point that Jose made actually about the current in this segment. This is problem 19 from chapter 27. I will publish this one. I will post this PDF file after I finish cleaning it up and doing everything I'm supposed to do in here. Anyway, it's still in LaTeX. Anyway, so I'm gonna post it later on. So basically, let me see if I can make this one bigger. Can I close this window here? It's not giving. Ah, it is. So basically, this is uh, the original problem. So the original problem had an EMF, a resistor, twice the resistor, three times the resistor, and four times the resistor. And we just followed the naming when we were solving it. I1, I2 coming through 2R, I3 coming 3R, I4 coming through 4R. And since we really did not have any good guess on where the current was going, if any at all, from node E to node A, so we labeled it I5. The question was, is that something to worry about because of the fact that I have zero resistance in here? Obviously, if there is a difference in voltage between the points A and E, yes, that's a problem because delta V is equal to Ri, and if R is zero because there is no resistor in here, then the current will blow up, will go to infinity, and indeed you will see smoke. But the only way to prevent that is if there is no potential difference between the points A and E. So in this case, you have 0 equal to 0 times whatever the value of the current in here. So this value can be any value that the system requires. And we proceeded. I'll be honest with you. If you ask any physicist to solve any mechanics problem, the first thing they will do probably is put F equals to ma and they start thinking through the problem, trying to find solutions. Same thing if you have an electrical system like this one, circuit. If you ask a physicist, they will start thinking in terms of loops, like what we did, and in terms of currents, and they start solving it. But if you ask somebody who is more into applied sciences or engineering or something like that, they see through it immediately and they figure out that there is actually a faster way of getting the solution. You will get the solution either way, so that you know. Had we proceeded with that yesterday, which was kind of lengthy at the end, we would have found the solution. And I think I'm going to dig into my notes. And I think there is actually something that I published in the past with a lengthy, basically, solution. Avoiding the matrices, avoiding all of the stuff that is coming from linear algebra, you could still do substitutions at the end. You will see your way through it. But apparently, I think this is actually better. This is the discussion we had, as I said, with three of you who hanged around a little after class. Noting the fact that E and A have the same potential. So that means that this resistors 3R and 4R are actually in parallel because they share one end on this case with the same voltage VC, and these 2 points are only one wire, 1 point. So basically we combine them, so the inverse of 3R and the inverse of 4R, the common denominator is 12, and 4 plus 3 is 7. So when you invert it, because remember that you're supposed to find the equivalent resistors between these two resistors, so at the end it turned out to be 12 over 7R. I put the approximate value in here. Please don't use it because you're going to get the exact value. The exact value will work out fine. So leave it as is. Then in this case, instead of having 3 loops with 2 nodes, bunch of equations, we only have two loops and 1 node because there is a redundancy in here. So the current I34 that comes in from this equivalent resistor will split into I2 and I1. And that's the same equation whether you say I2 plus I1 equals to I34 or you say I34 equals to I2 plus I1. It's the same kind of equation. So this is one equation. This is at nodes C or EA, whichever node you're considering. Then I have to consider loops 1. I took it this way, so whatever way you take it is fine. And I took the other one. I usually try to follow the current that is coming from the battery. So in this case, as I called it, I1 coming from the battery, and I2 coming from the other battery. So that's basically so this one turned out to be counterclockwise. This one is clockwise. Doesn't mean anything. I mean, the equations at the end that you're going to be working with are the same. So first equation, we could proceed with this whole problem symbolically. We really don't need numbers, to be honest with you, because we should be able to get everything in terms of R and the EMF. That's it. But at some point, we'll plug in the numbers to make life a little easier. So we have R I1. This is I started at point B. So R I1, that's the voltage drop, plus this voltage drop, which is this resistor 12R over 7 times I34. And then I'm rising potential in here, so that means I'm dropping by negative EMF. For loop 2, we start again from point D, so that means 2RI2 plus 12R over 7 times I34, here it is. And then by the time I come back in here, I'm actually rising potential. That means I'm dropping with a negative 2 EMF, because that's the value of the EMF in here is 2 epsilon. So these are the equations. The first thing you note in here, it doesn't matter what the value of R. If I multiply this equation by 2 and add the equations side by side, you will have 2RI1 and 2RI2. When you add them up, the 2R comes as a common factor, and you will be left with I1 plus I2. And then you will have here 2 times 12, that's 24, plus 12, that's 36. R divided by 7, the denominator is the same. So the only factor that changes is this factor times 2. So it's going to have 24 plus 12, that's 36. And everything is the same. Here you multiply it by 2, so it's going to be negative 2 EMF plus another negative 2 EMF, so we'll have a negative 4 of them. And when you move it to the other side, it's positive. So this is the equation by combining loops 1 and 2. Now, this number is I34. That's the node condition. So now, you have one equation that has I34 in here and I34 in here, which you pull it out. So you'll have 2 times R plus this thing times R. So you pull the R also out. So you have R I34. And then you will be left with the 2 plus 36 over 7. Therefore, I34 is basically whatever the common denominator in here, which is going to be 7. But you flip it on the other 7. 7 times 4 is 28. Don't forget the EMF. And then you will be 7 times 2 is 14 plus 36, that's 50. So that's basically what you end up with, 28 over 50. The EMF is 250. And that's nice, because 250 divided by 50 is 50. Oh, no, it's not 50. It's 5. I'm sorry, it's 5. 5 times 28 is 140. And what is left is R is 1000 ohms. So 1000 you just convert it into milli. So the answer is 140 milliamp. So you really don't need a calculator for this problem. You could do it manually, okay? So we found this current, which is the sum of these two currents, really, okay? Not really, it's, you have to be careful in here. So you have to, so it comes in here, split part of it into I34 and part of it into 3R and part of it into 4R. Okay, so since we know the current, I34, and we know the resistance, so we know the voltage. And we can find the currents I2 and I1. So that's what we need to do, because at some point we need to find this I5. So we really have to proceed all the way to get everything. So using loop 1, we got RI1 from this equation. RI1 is the EMF minus this whole thing. And we just found I34. So I34 is 140, I'm sorry, milliamp. The milli cancels the kilo. So it's just left with 140 divided by 7, which is 20 times, is it 20? 147 divided by 7? Yeah, it's 20. And don't forget you're going to subtract it from the EMF. So this is basically what the algebra is going to look like. So it's going to be the EMF times 12R over 7 times 28 divided by 50. And when all the dust settles, you'll be left with the EMF minus 24 over 25 EMF, which is 25 minus 24, which is 1 over 25. And the EMF is 250. 250 divided by 25 is exactly 10 volts. So the voltage across this end in here is 10 volt. Okay. No, I'm sorry. Yeah, that's 10 volts. Across this resistor. Here, I'm doing this segment. Why am I thinking the other one? So there is a 10 volt across this thing in here. So I'm sorry. I mean, hopefully you guys are going to do a better job than I am reading it right now. So using this in loop 1, we get, so it's loop 1, not loop 2. In loop 1, we have 250 plus our I1, which we don't know I1. That's the point that we're trying to find. I1 is plus this number, okay? Subtract this number from the EMF, you find our I1, and that gives you the opportunity to find I1 by just dividing by 1000. So the voltage itself, our I1 is 10 volt. That's the difference between these two numbers. And divide by 1000, which is the resistor, then you get 10 divided by 1000, which is a milliamp instead of an amp. So we're done with that. Let's do loop 2. It's similar. 2R I2, not R I2, because there are 2R in here, times I2, is equal to this EMF, which is twice epsilon, minus this voltage, okay? So you have twice the EMF minus 12R over 7 times 28, the EMF, divided by 50R. That's the value of the current that we just found. Here is the current, okay? So we could proceed, as I said, with symbolically solving this problem without subbing the values at the end of the day. Here is the values when you sub them to the twice the EMF, 24. So it's going to be similar, except 25 times 2 is 50. 50 minus 24 is 26. So we have 26 times 250 divided by 25. 250 divided by 25 again is 10 times 26 is 260 volts. So there is a 260 volt across this 2R. So when you divide 260 by 2, you get 130. But don't forget you have an R, which is a kilo ohm. So the kilo, when you invert it, it will become a milli. So the current in here is 130 milliamp. So we have I1 and I2. Now we can find I3 and I4, okay? Because remember, in this segment in here, if I can find the voltage, I can find I3. And I know what the voltage is. It's the same voltage across this point CE. Whether CE or CA or these are only 2 points. So if I find that voltage, all I have to do is divide it by this resistor, and I find I3. The same voltage divided by this resistor, I find I4. So at this point, we're home free, basically. So the voltage across the 3R, which is VCE, is equal to the equivalent resistor, 12R over 7 times this current that we just found, I34. Okay? And you proceed with the calculations. 12 times, because you have a kilo ohm, 12 times 1000 divided by 7 times the current, which is 0.14. We could multiply the milli by the kilo and cancel them, but we also could proceed this way, and the voltage is 240 volts. That makes sense, because there is a 250 volt in here, and there is 10 volts dropped in here, so there is 240 left in here. So that makes sense in terms of the algebra. We said also there is 500 in here, because you have twice times 250, that's 500. And from the 500, you're left with 260 in here, because we just found 260 in here. So there is a 240 in here to the totaling 500 on this side and totaling 250, because there is a 240 and 10, so that makes 250. So it makes sense. The voltage in here is 240 volts, okay? And it's the same voltage in here. That's 240 volt. And that should be the same voltage in here, 240 volt. So that's the same voltage, because they are in parallel. So again, we found that voltage. So we can find I3. I3 is just the voltage by Ohm's law divided by the 3R. 240 divided by 3 24 divided by 3 is 80. And then 1 over kilo is in milli, and the answer is in milliamp. And then if we go to the node condition, remember, the node condition at E now. E, you have a current that is coming that we just found it to be 80 milliamp. Here it is, I3 80 milliamp. And a current that is outgoing, I2, that we find it to be 130 milliamp. So here is 130 coming out and only 80 coming in. So this current, if I do the algebra, turns out to be negative. That means the current is coming this way. Because if you have 80, you need to add to it 50 to combine to give me 130. So we had the direction backwards, so the value should be negative. And indeed it is. Because I5 is I3 minus I2, which is 60 minus 130, it's negative 50 milliamp. So the current is not flowing from E to A, instead it's flowing from A to E, and its value is 50 milliamp. Now, just to check, this is not required because we already answered the question. We say the current is from A to E and its value is 50 milliamp. That's the question that you were asked. But let's check to see how much the value of the current in I4 should be. The I4, remember, is where the 4R is sitting. So again, we just figured out that 50 is going this way, 10 is going that way, so 10 plus 50 should be 60 coming down, 60 raining in, 50 of it is moving this way, and 10 of it is moving that way, and that should make sense. So that's what that I4 should be. It should be 60 milliamp. And the voltage, as I said, argued before, it should be 240 volts in here, and it is 240 volts in here, and we checked it. We need to check to see if this one also is 240 because they are in parallel, so it should be the same voltage, and that should answer the question that one of you guys raised during the point that, hey, if there is a voltage difference between these 2 points, shouldn't we worry that the current will be an infinite value? And it is. It should be. I mean, we should really worry. So the answer to that is the voltage drop between here and here is the same voltage drop between here and here. Therefore, these 2 points have no voltage difference. So if this was 240, and this we know it's 240, this also must be 240. Just to check, to make sure that indeed it's 240, we found the current I4, 6 milliamps. The voltage between C and A, between nodes C and A, should be just by Ohm's law, which is the resistance times the current. The resistance is 4R. And the current, we just said it's 60 milliamp. The milli and the kilo will make 1. And the ohm and the amp will make a voltage. 4 times 60 is 240. And that is indeed the checks. And we use the expression CQFD, Circuit Valid Demontre, which is basically what we needed to check. So the whole problem is self-consistent. Hopefully this video is helpful to understand how to proceed with similar problems. There is nothing wrong with the approach we took in the class. It was long, that's all. If you're familiar with the algebraic tricks and methods, that's the safest bet to go about these problems. Because in this particular case, you were kind of lucky. You had a situation that can be reduced into an easier problem. But imagine with me that there is a resistor in here, 5R for example. This will not work. This will not work. Because I can't say that the points E and A have the same potential because I have a finite resistor in here, so they are at different potentials. I don't have parallel stuff to work with. The 5R will not be the same like 3R, the 4R. So in that case, I really have to pull my sleeves and pull all the tricks I can, similar to how we proceeded in class. Just get loop 1, loop 2, loop 3, node 1, node 2. There is a redundancy in here in the nodes. Always there is one too many nodes. Okay? And at the end of the day, you will be dealing with 5 equations with 5 unknowns. Use whatever method you have, Kramer, or whatever method that you can think of. Matrices, anything. Substitution, that's how I proceeded in the past, and that's really the rudimentary method, which is usually not the shortest method in trying to find answers. But that's basically how we proceed in most of the circuits. It's the approach we had in class. That is usually the safest one. However, for this particular problem, it's an exception. It can be rendered easier. And it's not always like that. So I hope that you guys understand how the answer was found for this problem. And it's a good problem. If you understand this problem, you understand a lot about circuits. If you have any doubts and questions, please reach out. Thank you.